Hey everyone, welcome back to another AP Pre-Calc video. Today we're going to be covering lesson 2.10. Let's get right into it. All right, so here's the bell ringer. Pause the video if you haven't done this already because I am about to go over the answers. So we want to evaluate the following expressions, and so what we have here is a bunch of different logarithms, and we want to get them into real numbers. Positive, negative, fractions, integers, doesn't matter. But really what this is asking 3 to what power will give us 9? And that's going to be 3 squared. So 2 is going to be our answer for the first one. The next one we have ln1. This is the same thing as log base e of 1. So e to what power gets us 1, which is to the power of 0. Anything to the power of 0 should be 1. This is going to be r to what power will give us 7, or r to the 7th, which is just to the 7th power. Now we have the next two are going to be pretty tricky. 25 to what power will give us 1 over 5. And so we need to ask ourselves, will give us 1 over 5. How can we go from 25 to, let's just say 5 to start with, right? We know the square root of 25 is equal to 5, and this is 25 just to the 1/2. Now, how do we move that 5 to the denominator? Remember, when you take anything like 25 to the 1/2 and you make that exponent negative, it basically moves that 5 into the denominator. So this should be our answer, negative 1/2 there. And then finally, the toughest one, and you won't see anything like this on a possible test or quiz. This is just to get you familiar with these fractional exponents. 16 to what power will give us 64? And so 16 doesn't go into 64 a nice number of times. So what we need to do is convert to a common base. And so looking at these two numbers, a smaller number that is multiplied a nice number of times into both of those is not only 2, but 4 as well. So I'm going to go with 4. I know 16 is 4 cubed. And then I know 64, or 16, sorry, is 4 squared, and 64 is 4 cubed. So this is 16 to what power will give us 64, which is 4 cubed. And so we can simplify this and basically just solve for x. So 4 to the power of 2x equals 4 cubed. And then here, we are going to set these two equal to each other. So 2x equals 3, x equals 3 over 2, and so that should be our answer there. You can use a calculator for this one if you need, and you should get 1.5 or 3 over 2 as well, no matter what method you use there. All right, so before we begin, grab a piece of scratch paper if you're watching this video for the first time, and we're going to fill in this table. And so here our equation is 2 to the power of x. This is an example of an exponential equation, and then here we have log base 2 of x. This is going to be an example of a logarithmic equation. So 2 to the power of x, we have 2 to the first is just 2, 2 squared is 4, 2 cubed is 8, and then 16. And now what we have here is this is the same thing as asking what is log base 2 of 2, or 2 to what power gets us 2? That's 1. 2 to what power gets us 4? 2 squared, 2 cubed, and 2 to the 4th. So one thing that I want you to realize is if you have 2 to the x and then you have log base 2 of x, the base in both of these is going to be 2. Remember, this small subscript is your base, and then obviously this is your base of an exponential. They're both 2, and they both have flipped their x and y values. So the exponential and the logarithmic could be considered potential inverses of each other, right? Remember, inverse equations, x and y values flip, and we will be exploring that more today. So just like how we can graph previous functions, we can also graph logarithmic functions. And I know in the past we've done, you've learned absolute value, you've learned possible quadratic equations. Now we're going to be graphing logarithmic, and there's two different types of logarithmic. The first one is going to look like this, and then the second one is going to look like that. Those are the two general shapes you'll need. The equation is y, or f of x, equals a times log base b of x. and that's our equation. You can replace y with f of x. It's the same thing. And now there's three restrictions, right? There's three criteria that we have here. And so let's look at each criteria kind of in depth. The first one is where b is going to be greater than 0. Now, why do we want b to be greater than 0? Because let's say we had a times log, and then let's say b was a negative number, right? Negative 3 to the power of x. Sure, you could do negative 3 squared, right? That's obviously 9. You could do negative 3 cubed. That's obviously negative 27. But with a function, we want to do fractional possible exponents. And so what would negative 3 to the power of 2.5 be? And that's something that even I don't know. And so that's why we kind of just want to stay away from that situation where you have negative numbers to the power of a fraction. And so we're going to basically say, nope, our base has to be a positive number. The next criteria is our base is not equal to 1. Why is this important? Because if you then have 1 in for b, this is a log base 1 of x, and it doesn't matter what x is equal to, 1 to any power will always give you 1. So x has to be 1 here. So this is just a case where x is only going to be equal to 1 because you can't have anything else in there that would make sense. And then the final criteria is this a is not equal to 0, or a is not equal to 0 there. This is really because if you have a log base b of x, 0 times log base b of x, doesn't matter what this is, the whole thing should be 0, because 0 times anything is 0. So that's why we just say, hey, a can be a positive number, a negative number, a fraction, a decimal, just cannot be 0. All right, so remember, because exponents and logarithms are kind of inverse operations, exponential and logarithmic functions are going to be inverses of each other. Therefore, just like inverse functions that we've learned about last semester, the input-output values of an exponential turn into the output-input values of a logarithmic, which means our x and our y values for an exponential turn into our x and y values for our logarithms. It's just they're kind of flipped. And that's what we saw in the previous example there. So this is 2.3. Remember, for exponential functions over equal length input values, right? So these are equal length. They're all 1 apart. Plus 1, plus 1, plus 1. The output values change proportionately or multiplicatively, but we'll use the word proportionately here. And in this case, if you take a look here, it's changing proportionately, and then the words we used were by a factor of 2. And this is obviously the exponential function we looked at before, just 2 to the power of x. Now, for logarithmic functions, the x and y values are flipped. So now our input values change proportionately. And if we take a look here, we see that to go from 1 to the next, you're multiplying by 2 times 2, while our output values now are equally spaced, plus 1, plus 1, plus 1. And so notice how they are switched. They still have like the same criteria as an exponential function. It's just our x and our y values are flipped. And this is the logarithmic function of log base 2 of x, the flipped version of 2 to the power of x. So those two are inverses of each other. Now example number 1. We have 4 tables shown below. Determine if it's logarithmic, exponential, or neither. So here we see our inputs are equally spaced, plus 1, plus 1, plus 1, and our outputs change proportionately. It's a multiplication factor, and it's not by 2 or divided by 2. It's times 1/2 is what we want to say here. Doesn't matter, though, if it's 1/2 or 2 or whatever number. As long as it's a multiplication rule, this is going to be an example of an exponential function. Now let's take a look here. From 10 to 30, you multiply it by 3. From 30 to 90 times 3, 90 to 270 times 3. So it's a multiplication rule in our x's while our y values are equally spaced. This time they're spaced by 10 apart. And so this is going to be an example of a logarithmic function. Now let's take a look here. For C, we see when you see your values grow bigger drastically, it's probably going to be a multiplication rule. So this is going to be times 10, times 10, times 10. So multiplication rule here. Then we also see times 2, times 2, times 2, a multiplication rule here. So is there a type of function that we call for both of them or multiplication? Not yet, so we'll just call that neither for now. That would not be considered exponential or logarithmic. And finally here, we see times 2, times 2, times 2. And then here, this is minus 3, minus 3, minus 3. That's okay, even if they're going like that. It's just not usually what we see, but that's still fine. You see a multiplication rule here and an addition rule there. So this is going to be an example of a logarithmic function there. So those should be our 4 answers: exponential, logarithmic, neither, and then logarithmic again. All right, so this question will return. This is the final time that you will kind of see this question. And so it's where I give you a table. For those of you that were here last semester, you've seen this, you've had lots of experience with this. The function f is defined for all real numbers. The table gives values for function f at selected values of x. And then it's a two-part question. Part 1, based on the table, which of the following function type best models this function, either linear, quadratic, exponential, logarithmic? And then part 2, give a reason for your answer based on the change in the outputs and the change in the inputs. Refer to the table in your reasoning. So this, we see our inputs are proportionately changing, right? They change proportionately. And so it's times 2, times 2, times 2, times 2. But the main thing is you see a multiplication rule in your x values. In your y values, though, these are equally spaced. They're all spaced apart by 1, plus 1, plus 1, plus 1. So that's an addition rule. So this is going to be always modeled by a logarithmic function. And then for our reasoning, you can say, as the input values change proportionately by a factor of 2, the output values are equally spaced. You don't have to even say the by 1 part, but you can. Make sure it's correct if you do, or increase at a constant rate. Either one of those would be fine, but that would be a perfect answer to give for your explanation. So try example 2 on your own if you haven't done this yet. And so let's take a look. Let's work through this together now. Here we see our outputs are changing proportionately again. So here from 60 to 30 you're dividing by 2, but we don't like to say dividing, so instead we're going to replace that with times 1/2. 30 to 15 is also times 1/2. 15 to 7.5 is times 1/2. And then you would get a calculator. So 7.5 to 3.5 is times 1/2 or divided by 2. Now let's take a look at our inputs, right? Our outputs are equally spaced. Plus 3, plus 3, plus 3, plus 3. And so this is going to be a logarithmic function. And then what is our reasoning for this? And so I would say over equally spaced outputs, instead of inputs this time, the inputs change proportionately by a factor of 1/2. And so that would be a perfect explanation. You talk about how the inputs change, which is proportionately. You talk about how the outputs are equally spaced, and you even give the factor that the inputs are changing. We just really want that multiplication factor. The addition factor, not so important in this example here. All right, the next thing I want to go over is talking about how exponential and logarithmic functions are inverses of each other. So we kind of looked at that earlier by seeing the two tables and seeing how one was like 2 to the power of x and the other one was log base 2 of x, and they were inverses because the x and the y values were flipped. And so that's not just going to be the case with that function, but if you have any base b to the power of x, its inverse function will be log base b x. So remember, these are both the bases for each one, which is why they're the same number. But those are going to be always inverses. You won't need to know anything more complicated than that. Also know if you have those two functions, let's say 2x and log 2x, if you plug one into the other for x, or vice versa, if you plug this into x here, you're going to get x as your output there. And that's the case with any inverse function. Now, two more important properties of inverse functions are graphs of inverse functions are always going to be reflections over the line y equals x. So for example, this is what that line would look like. Same thing here. And so like we explored in 2.8, if you have a quadratic function, that's going to turn into a square root function with its inverse. And then if you have, let's say, a logarithmic function, like so, that is going to be an exponential growth function like that, is going to be its inverse there. And so that's just an example graphically of how they're inverses over that line of reflection because you are flipping or switching the x and y values. The other thing to know is if you have just the original function and then its inverse, if on the original function we know there's a point, let's say just x comma y, on the inverse, y comma x has to be a point. So for example, let's say 2 comma 4, on the inverse, 4 comma 2 has to be a point. All right, example number 3. With that rule that we just learned, find the inverse of each function. So this is just going to be log base 4 of x, right? When you have b to the power of x, the inverse is log base b, of x. So then the inverse should be 5 to the power of x. This is a little weird because we see something in the exponent. So let's see if we can rewrite this. This is 9 to the power of x over 2, which is the same as 9 to the power of 1/2. And this whole thing to the power of x. 9 to the 1/2 is the square root of 9 to the power of x, which is 3 to the x. And remember, this is still g of x. We didn't change anything. We just rewrote it. And so the inverse should be log base 3 x. And now that I think about it, let's put the correct notation for each of these. There we go. There. So those are our 3 inverse functions for those 3 examples. All right, example number 4. This is showing how f of g of x is equal to g of f of x, which is equal to x only for inverse functions. So we're going to look at that now and show that 3 to the power of x and log 3x are in fact inverses. So first, let's find f of g of x. This is where we plug log base 3 of x into x in there, and then simplify as much as we can. So this would be 3 to the power of log base 3x. And remember, the log and the exponent cancel each other out to just give us x. Now let's find g of f of x. This is going to be a little bit reversed because we're going to take f of x now and plug it into g of x. This is equal to log base 3 of 3 to the power of x. And remember, those cancel out as well to just leave us with x. So because both of those give us x, these two are inverses. So it does work. All right, so example 5, a portion of the graph of the exponential function 2 to the power of x is shown. Sketch a picture of log base 2 of x, or the inverse, on the same coordinate grid. So here what we want to do first is let's find a few key points. So we see 0, 1, 1, 2, and 2, 4 are nice 3 integer points. So let's writing those down. We have 0, 1, 1 comma 2, 2 comma 4. I want to find all three of these on, let's see, the inverse. So to do that, we just flip the x and y coordinates. Once we have this, we can plot them. So 1, 0, 2, 1, 4, 2. That's perfect there. And then what we want to do is taking a look at this, we see that this is going to shoot up forever. And so the inverse will probably go like that. And then if we take a look at what happens when you go to the left, though, this gets closer and closer to 0. So if we kind of flip that, this should get closer and closer to the y-axis, that negative y-axis there. And so this is what the inverse should look like, or a logarithmic function should look like, with that horizontal asymptote being reflected and turning now into a vertical asymptote for logarithmic functions there. All right, example number 6, we have an exponential function. H of x is a to the power of x, and this has 2 points we're given, 2, 3 and 6, 27. And then we want to use this to find the rate of change over y equals log base a of x on the interval from 3 to 27. And so what is this function? Well, we know from the formula that this is actually the inverse of h of x, which means on this function, our 2 coordinates shouldn't be 2, 3, but should be 3, 2 and 27, 6. Once we have this, we want to find the average rate of change on this interval, which is, this is a fancy way of saying we want to find slope between those 2 points. So let's plug it into our slope formula. Remember, our slope formula is y2 minus y1 over x2 minus x1 is equal to m. And then we're just going to plug those 2 points in. So we have 6 minus 2 over 27 minus 3. This is 4 over 24, which will simplify to 1/6, and that should be our answer for example number 6 there. All right, and then finally, example number 7. The function f of x is given. Which of the following points is on the graph of the inverse? And so here we see 1, 0. We see 4, 1. And so let's see if we can find the inverse here. The inverse should have 0, 1, should have 1, 4. Unfortunately, none of these are going to be any of our answer choices. They all have a point 2, 8, 2, 16, or the inverse or the flipped version of both of those. So let's take a look at maybe what our next point would be. Well, we see here our outputs, our inputs are multiplying by 4. So let's multiply that by 4 again to get 16. And then here our outputs change at a constant rate. They're equally spaced. So here it's +1. This should be +1 too. So looking at like that XY table, right? Here, if you have 1, 4, and then 0 and 1, this is times 4. So this should be times 4 to get 16. And then this is +1. So this should be +1 to get 2, because we know this is a logarithmic function. So 16, 2 should be a point. However, we want to find the point on the inverse, which would be that, but flipped. So B should be our correct answer here. This is a pretty tricky question, so just make sure you pay attention to the wording, because a lot of times they'll give you an original and ask you something about the inverse function there. All right, if you have any other questions, please come see me in office hours, and I will see you guys later. Thanks.